Sure. So, Piyush, okay. Yeah, so we're very happy to have Praneeth from Google India. Praneeth is very well known for a lot of foundational work on optimization, non-convex and convex, statistics, learning theory, and machine learning. And today he'll be telling us about efficient inference or designing others to be more efficient by inference.
Firstly, thank you for the invitation to speak in the seminar, and thanks Piyush for the introduction. Yeah, so I cannot see raised hand. So if there are any questions, just call out in the middle of the talk. Also, like the talk that I'm going to give right now is mostly empirical. There will be no theorems or like no proofs. Hope it'll still be interesting. Okay. So I'll be talking about inference efficient LLMs, and this is a joint work with like several of my wonderful collaborators from Google DeepMind. And before I get there, like I wanted to give a brief introduction to some of the paradigms in machine learning, and specifically those that are like very popular right now, and also like the transformer architecture. And hopefully this will not be boring or like repeating like information. Um, if you feel so, you can just let me know and I can try to speed this up. But I wanted to first give a brief overview of the things before I go into the details, because unless like we understand the setting in which we're talking about inference efficiency and so on, like whatever I say later might not make sense. Okay, so ML is broadly learning from data, and currently I would say like there are two dominant paradigms among many others, but like currently two dominant paradigms that are driving like the modern machine learning and artificial intelligence wave of artificial intelligence. So the first one is supervised learning again. So maybe like most people should be familiar with this. So given training data x1, y1 all the way up to xn, yn, so we have n training examples. So each xi, yi is a training example. So xi, we want to take it as an input, and then we want to be able to predict yi given xi, right? And so what this means is that we want to learn a function f, so that given a new data point x, we want to compute f of x. So f of x should be similar to what y is. So x can be a question and y can be an answer. And the second paradigm I want to highlight is what is called generative modeling. So here we are given training data, which is just an example, so x1, x2, all the way up to xn. Say they are sampled independently from some underlying distribution denoted by P. So the goal is that we want to learn a sampler Q, so that when we press a button, meaning that maybe we generate a Gaussian random vector and we give it as an input to Q, then it will produce a sample which will be essentially like as if it's being sampled. We are sampling a new point from P, right? So x1 all the way up to xn could be like a list of existing proteins, and then we want to be able to generate new proteins, which still makes sense from like either biological, chemical, or physical point of view, right? And conditional generative modeling is a combination of both of these, where we want to condition the generation process on some maybe what is called covariate. So let's say we want to condition the generative process on xi. So given xi, we want to be able to sample from a conditional distribution of p of whatever we want to sample, conditioned on xi, right? So like again, we are given like training data samples xi, yi, and we want to learn this conditional distribution sampler. And here we can think of x to be some property, and then y is a protein which actually satisfies that property. So we want to be able to sample a protein which actually satisfies that property, right? So large language models can be thought of as conditional generative models. And in particular,
wait, go back one slide.
Yeah.
It's a combination because you're trying to supervise, you're trying to do supervised learning on the distribution, and then you're trying to sample. Why is the combination?
Because like in supervised learning, you usually think of like you give an image and then you want to say it's a cat image or a dog image, right? So there is no distribution that you're outputting. You're just saying it belongs to this particular class. Here, you don't have a single correct answer. You're actually trying to generate a sample from some underlying distribution. So this is a combination of both of these, because yi is not like a fixed thing, but rather yi is actually being sampled from some distribution which is conditioned on xi. Does it make sense?
So then it's just like the second thing, right? Why is it like the first thing?
I guess like the conditioning is all I'm talking about here. Where like here you did not really condition on anything, like it's just some underlying distribution. Here you want to be able to learn like several conditional distributions all at once.
Is there any connection between the distribution?
Yeah, usually there will be connections between the distributions.
Okay.
Because I mean, like even if you just take like X is a property and Y is a protein, like different properties might be related to each other. And overall, like all of them are still like from a marginal point of view, like all of them should like eventually produce something which is actually a protein, right?
Okay.
Yeah. So in the context of yeah, so what I wanted to convey was that large language models are conditional generative models where we give a prompt, which is basically what you are conditioning the model on, and then you want to generate a response which makes like which corresponds to the prompt that we have given as an input, and like these are usually very large models and trained on very large corpus of data. So just to give some examples, so this Llama 4 models come in three sizes, and all of them have been trained on about 30 trillion tokens. And a token can be thought of as a word, but usually maybe they can be part of a word as well. But for all like practical and intuitive purposes, we can think of them as a word, and trained for several days on like thousands of GPUs. And usually like the training process consists of two stages. So in stage one, we train these models, like most of these 30 trillion tokens would be coming from the stage one, where we are using like a loosely curated collection of pre-training data. And this would be curated by just crawling the entire web and collecting data. And because this is so uh, large in magnitude, it's hard to do like very good quality control in terms of like what kind of data you're using, whether it's meaningful, not meaningful, and so on. So there'll be some uh, broad ways of doing like ensuring that like the data quality is good, but it's in general like hard to make sure that like the tokens like all the tokens here are of very high quality. And then in stage two, usually like the amount of data used in stage two is much smaller, maybe like uh, say three orders or four orders of magnitude smaller. And here like people would usually use like much more carefully curated instruction tuning data, and also maybe like other data like code, math, or like whichever kind of uh, tasks that we want the model to do well on. So the second stage usually is very carefully curated and is like much smaller compared to the data that we have in stage one. And like for Llama 4, like there's also a blog post with a lot more details. So I now want to just briefly explain like the model and the loss functions that are used in training these. So LLMs are trained using the next token prediction loss. Again, like token, maybe we can just think of it as a word. So let's take a training example. So if we think of this Jack and Jill went up the hill, like this, let's say is a training sentence. What we want to do is we want the model to take like it's parameterized by f theta. So theta are the parameters. So we wanted to take a token sequence and then output a token. And was there a question?
No.
Okay. So we want to take a token sequence and then output a token. And here like theta are the parameters of the model. So okay. So here the token sequence would be like Jack and Jill went up the, and then we want the model to be able to predict what the next token is going to be, which is the hill, right? And in order to train the model to be able to do this kind of prediction, we use a loss function which takes the output token that the model predicts and then the actual ground truth token, which is the hill here, and then we will give a loss which is between 0 and infinity. And if the tokens are identical, then if the tokens are close enough, we want the loss to be small, and if the tokens are far apart, we want the loss to be large, right? And as such, when we measure the loss on these discrete sets, it doesn't make sense. Okay, so the objective is like minimizing theta, this loss of theta. and the input is Jack and Jill went up the and the output is Hill. Yeah. So as such, when we measure like a distance between the output token and Hill, like for these discrete settings, we can only think of this Hamming kind of distance, where like if it's exactly the same as the ground truth token, we have a loss of 0, otherwise 1. But this is discontinuous, and we don't know how to train it, and so on. So also because like there could be many other continuations that might still be valid, and even though Hill might be the most popular completion, like there could be other things which ensure that the sentence still makes sense, right? So for this, we want to be able to output not just a single token, but rather we want to be able to output a distribution over tokens. So for example, like Jack and Jill went up the hill makes sense, Jack and Jill went up the stairs also makes sense. So we want to output, like the model to output a probability distribution over all the tokens, including hill, stairs, and all possible words. So the set of all possible words is called a vocabulary. So we want the model to output like a probability distribution over the entire vocabulary. And yeah, so it outputs a distribution over like all the tokens in the vocabulary. And L is usually taken to be the KL divergence between the two distributions, one distribution being the output distribution over the entire vocabulary size, the other distribution being the delta distribution, which puts a mass of 1 on the token that actually appears in the training data and 0 on all the other vocabulary items. Any questions until here?
So Praneeth, so typically wouldn't you want the notion of similarity between the next token that is predicted and what you actually wanted the token to be? That's also context dependent, right? I mean, in the sense that
Yeah.
Yeah, okay. I just wanted to.
Yeah, so it is context dependent here because the model, like this F theta, is actually taking this entire thing, Jack and Jill went up the, and then it is predicting what the next token should be. So
no, but my question was more about the loss function L. Is the loss function like sort of is the token sequence also a part of the loss function or no?
No, token sequence is not part of the loss function.
Okay.
Here we are just doing. I mean, essentially, if we were in the discrete world, we are doing a Hamming distance.
Okay. Okay.
And because like there could be multiple options, like you cannot say that like the output has to be only Hill, because it could be something else as well, right?
Okay.
We take a probability distribution and then take the KL divergence, but otherwise, like we don't use the context information while computing the loss function.
Is there any reason for using KL divergence and not maybe some other system?
I guess like in ML literature, this is usually called the cross entropy loss, and there have been multiple. I mean, in the recent past, I don't know of like any ablations or studies which compare like different loss functions. But in the past, people have compared like the squared distance versus cross entropy loss and so on. And people observed that cross entropy loss works better. And one of the reasons that people propose for why the scale divergence or cross entropy loss works better is when the like predicted thing becomes close to the ground truth, uh, like the gradient of the squared distance goes down much more rapidly compared to the cross entropy loss. So towards the end of training, it seems like cross entropy loss people have observed to train better compared to using the squared distance.
I have a question. So, between these tokens, why are we taking instead of the Hamming distance? Wouldn't it make more sense to take the distance in the embedding space or something like that?
So, like right now, we don't have any, like this one is just starting from scratch. It's not really relying on any, like any other model to say which words are close, which words are not close, right?
I see.
You're just starting from like raw text, and then
Yes.
yeah.
But that can also be done.
I mean, in
Right?
some sense, for example, like if you see that there are examples where hill and stairs are co-occurring, like hill and stairs are both possible completions for a lot of sentences, right?
Yeah.
And it will automatically bring the embeddings of hill and stairs closer together, because just
I see.
like Jack and Jill went up there, you cannot be sure whether the next word is going to be hill or stairs.
I get it. Yeah.
So it will happen as part of the training process here.
Yeah.
And like there are other models which have trained this using different loss functions and so on. But here, like LLMs, usually like they just try from scratch. They don't really build on top of some other BERT or some other previously trained model. Thanks for the questions. Yeah. Okay. Any other questions? Okay. Okay. So okay. So we saw that like we give all of this context and then we predict this particular like the next token prediction, right? Actually, can you see my cursor?
Yes.
Yes, we can.
Okay. Yeah. So you can we can see that yeah. So we give all of this context and then like we'll predict like the next token. But using like if we just do it in the naive way, then we will end up getting only one training example in a given sentence, right? But this single training sentence actually has multiple examples. What I mean by that is that given Jack, I want to be able to predict and given Jack and I want to be able to predict Jill, right? And given Jack and Jill, I want to predict Went, like that. So as such, this single sentence can give me like 6 training examples. It turns out that I can uh, do the gradient computation and use all of these examples in parallel so that the overall computation during training will be the same as whatever I would have done if I had used only this particular example. Right. So the yeah. So the point I want to make is that even though we are talking about doing the next token prediction, it's actually very dense in terms of like information, because even in a single sentence, we can actually extract multiple next token. Like for every, we can condition on after every token and then say what is the next token. And this gives us a lot more training examples to train on compared to if you were able to train on only one. And this also improves the efficiency of the training process. Does this make sense? Any question about this?
So gradient has to be computed for each term separately. Each term.
Yeah, gradient has to be computed for each term separately, but actually maybe this will make more sense after we go over the transformer architecture. But the point I wanted to make was that we do only one forward pass for all like this entire sentence. And based on that, we will be able to compute all these loss functions. So we don't have to do 6 different forward passes for this computing these 6 different loss functions. We can compute all of these by doing just one forward pass over this entire sentence.
I can think of even more examples here, right? Suppose you're given Jack and blank went up the hill, then you can try to predict blank or things like that. You can also use future information. Why just the past information?
Okay, so are you talking about mask language modeling, that like, maybe you mask like random words and then words at random positions, and then you ask to predict them given the rest?
Yeah.
Yeah. So like there are those models. So BERT is probably, I mean, BERT is the maybe the most popular masked language model. So the reason these LLMs are autoregressive is if you want to use them to respond to user requests, or like you say something and then like the model wants to respond with something, then it is uh, it is more like continuation rather than masking, right? So if you train a model to predict masked words, it might not be able to do well in terms of like responding to a question, because does it make sense?
A little bit, yeah.
Yeah, I mean, mask language modeling is primarily used for, okay, so mask language modeling is primarily used for doing representation learning. So you want to learn representations or embeddings, say word to vec, text to vec, these kind of things, sentence to vec and paragraph to vec, doc to vec, and so on. But we cannot use them directly off the shelf to get answers to questions and things like that. Whereas this autoregressive generation is exactly like will exactly be able to help answer questions if we directly ask the questions.
Okay.
Yeah. Okay, so let me briefly explain like the transformer architecture. So it has multiple layers. So we have like embeddings, attention, feed forward, and softmax. Okay, so actually, let me go into the transformer architecture in a bit more detail in the next slide. But just taking like the previous example, what the transformer architecture does is firstly, like we broke up the sentence into tokens. So Jack is a token and Jill went up and so on. So each token first gets embedded into some vector in some, say, 1000 dimensional real vector space. So we have a corresponding vector, which is xjack. So all of these are trainable. So what is the vector corresponding to Jack? That's a trainable parameter. So we have xjack. Then this goes through attention and feed forward layers. So these are usually repeated, say, some number of times, say L times. And then finally, we have a softmax, which takes in the vector, which will be in the same dimension that we have here. So we input a vector. Each of these transforms that vector into some other vector in the same dimension. And finally, we get some other vector in that same dimension. And then we multiply it with the embeddings corresponding to all tokens in our vocabulary. And then we will do some normalization to get probabilities assigned to each of the next tokens. So here maybe like Ease has probability 0.1, Jill has 0.2 probability, and has 0.6. And then we have the same thing. And this is a probability vector that we get as output. And this is where we apply the loss with respect to ground truth. Okay, so the key components of a transformer are the embedding or softmax layer. Then there is a feed forward layer, and then there is an attention layer, right? So in the embedding or softmax layer, as we said, like we have each word and token, it's assigned some particular vector in this 1000 dimensional space. And this is again independently applied to each token. So each token's representation is independent and has nothing to do with some other token's representation as a parameter. Like through the training process, it's possible that like two representations come close because they are semantically similar, but as such, like there is no constraint binding them in any way. Then there is a feed forward layer, which takes in a vector x and then multiply. So the parameters are w2 and w1. So we multiply the input vector x with a matrix w1. We'll again get a vector. We apply an element-wise nonlinearity given by phi. And then we again multiply this by another matrix w2, and then we get the output of that layer, right? This is again applied independently for each token because this w1 and yeah, so this does not really couple token at a previous position with the token at next position and so on, right? So then there is finally this attention layer, which is actually the key innovation in transformer and is the one which actually couples different tokens and synthesizes like the contextual information given in all of the previous tokens that we have seen so far. Okay, so let's look at the attention mechanism in a bit more detail. So let's say we are given input tokens or input embeddings x1, x2 all the way up to xn. So we are given n things as n vectors as input. And the attention layer has three parameter matrices. So they're called query, key, and value matrices. Okay. So for each of the tokens here, so let's call xi. So for the ith token xi, we compute the query to be qi to be q times xi. Its corresponding key is k times xi and corresponding value is v times xi, right? So when we are given all the previous tokens x1 to xi, the attention operation, it transforms the like ith token xi to be summation j equal to 1 to I. Again, like this I is because of causal attention, meaning that a token can only attend to all of the past. There are also bidirectional transformers, but like LLMs are predominantly the like the causal transformer variants. So j can only go from 1 to I. So we want to be able to combine all the previous value functions. This is where the contextual information comes from, with weights that depend on the current token as well. So we have Pij, Vj. So we have a weighted combination of all the values from the previous tokens. And Pij is given by usually taken to be it's proportional to exponential of qi times kj. So qi is the current query. So xi has a query qi, and then the jth embedding vector xj has a corresponding key which will be kj. So we take an inner product of qi kj and then take an exponential, and then the z is just a normalizing factor to make sure that this is a probability distribution, right? So we take a weighted combination of all the previous value vectors, Vj, and this is, yeah, so this is just normalization factor. Yeah, so this is basically the attention mechanism. And the key idea is that the future tokens attend to all of the past tokens. They look at what the past tokens were, and based on that, they're able to update their representations, right? And there are many additional aspects, such as like we can take multiple heads and then combine the outputs of these multiple heads. And here we are looking at causal because j goes only from 1 to I. Bidirectional would have had j equal to 1 to n. So there are many variants, but this is the basic and fundamental formulation of a transformer, of the attention layer in a transformer. Any question on this?
And this n is some parameter of the model. So
Yeah, n is a parameter of the model. It's usually called sequence length. Yeah, sequence length, context length. Yeah.
And then you just shift by 1 after generating.
So yeah, so maybe we'll come to the generation part like when we look at the inference, but this will be applied for each position independently. So I can be anything from 1 to n here. Does that answer your question?
Yeah, okay. So suppose something has to be generated, so that's the n plus 1 thing here, or the nth one here.
Yeah, n plus 1th one will be generated, and there I guess like the input to, maybe like you are giving xn as an input, and then you are generating like the output here, and then you will feed that output. You will sample and predict what the next token is going to be, and then you feed it back as input to the next time, and then you'll repeat the same process. Yeah, this is during inference. So during training, we don't do any kind of sampling or incremental thing because we have like all the tokens available to us right away, right? So we can just use mask. So when we are looking at this output and we are looking at this attention only considers like this token. And this attention will consider like both of these tokens while doing its attention. This attention will consider all the 3 tokens and so on. So we don't do it auto-regressively during training, but during inference, yes, we do it auto-regressively. During training, we just take the entire thing and use attention mask to make sure that this token is not attending to the future.
And all the training examples are smaller than n or something.
Yeah, you chunk like the training examples to be smaller than n, yes. Any other questions? Okay. Okay, so yeah, so that was the background I wanted to share. And now let's talk about inference efficiency. So in efficiency, there are 2 aspects. So one is training efficiency, the other one is inference efficiency. So I hope the names are clear. So so LLM has a training phase, and then once the model is trained, you want to deploy them where people can use it. So the efficiency during the first part is the training and efficiency, and the second part where we are doing inference with the model. So that's the inference efficiency part. So training is a one-time cost, whereas inference is a continuous cost and will be there as long as the model is deployed. And there are estimates which suggest that over the life cycle of a model, inference cost accounts for about like 80% of the overall cost of the model. And high inference cost is one of the biggest hurdle to deployment of some of the most capable models, even like including like the reasoning models like O3, O1, O3, and so on, which generate like lots and lots of tokens. And yeah, so improving inference efficiency is a very active area of research. And there are ideas across like several domains, including algorithms, architectures, systems, hardware, and so on. And in this field, okay, so before I go to our work, so let me quickly explain like what is the challenge in inference compared to the training part. So during generation, one of the biggest challenge is that the models have to generate tokens auto-regressively. What I mean by that is that once we give an input, which is say, what are Himalayas? So if this is our query and we give it as a prefix, so the model processes all of these using attention feedforward softmax and then produce the first response token, right? And then it takes this response token, feeds it as an input, and then gives the second output token. And it does this sequentially. And this cannot be parallelized because we want the output of the previous step to be actually fed in as input to the next step. And so these as such cannot be parallelized, and we are essentially like doing this sequentially, right? And also, like, there are different components within this model, like attention feedforward and softmax layers, and we want to be able to speed up all of them. So why is this autoregressive generation a bottleneck? Because machine learning accelerators, meaning like GPUs, TPUs, they're optimized for very efficient matrix multiplications. And even if you do matrix vector multiplications, which in terms of number of flops, number of operations required is much lower compared to a matrix multiplication, it still takes the same amount of time as a matrix multiplication, right? So we are not able to effectively utilize the full power of these GPUs or TPUs, because whatever time they were able to do matrix multiplication, we are ending up doing only matrix vector multiplications, right? And this autoregressive generation actually leads to matrix vector multiplication, because if you look at the feed forward layer, we said like it has the following form: W2 phi of W1x. And if we are only processing one token at a time, so x is a vector, so we'll have a matrix vector multiplication here. This will again be a vector, and then we'll have another matrix vector multiplication. Similarly, in the attention layer, we again have matrix vector multiplications, because the key component is in computing this inner product of qi and kj. And if we only have a single I for which we are computing this attention probabilities now, then we have all of the past kjs, which will be a matrix, and then we are multiplying only with the current qi. So this will again be a matrix vector multiplication, right? So this cannot exploit like the efficiency that these hardware like GPUs and TPUs can provide. So in order to help make this more efficient, so we designed two approaches. One is called HiRE, and the main idea here is to make them more efficient in autoregressive mode by using sparsity. And the second approach is like actually mitigating the autoregressive nature of LLMs itself, and the approach is called tandem transformers. And the main idea is that we want to use a small language model in autoregressive mode and augment it with a larger model that can be run in block mode. And in this talk, I'll primarily be talking about the second work, which is on tandem transformers. But if people are interested, they can look at the first work. So it's on archive. Actually, any questions before I start the second part about autoregressive generation and why the bottleneck is there? Okay. Okay. So as
in fact, like I was just about like one way to see the bottleneck is to try to run Llama on a CPU, which I have done, and then you see the bottleneck in front of you.
Okay.
See one word after every 20 seconds.
So it took 20 seconds to generate one token.
You run Llama on a CPU. So not 20 seconds, but like 5 seconds, like one word every 5 seconds. You see.
Okay. Yeah. Okay. So just recalling like autoregressive LLM inference. So we have this query. So describe the Himalayas. So it generates some query representations, and these are then used by the attention layers of the model to like while generating all the future tokens, right? Like it takes Himalayas and then produces the and so on. So the main research questions that we wanted to understand was this autoregressive generation leads to poor utilization of GPUs and TPUs, as I just mentioned, because it uses only matrix vector multiplications. And so we wanted to understand whether we can mitigate the autoregressive component. The second question that we wanted to understand was that conceptually, like LLM wants to do two different tasks. So one is understanding the query, and the second one is generation, so generating like the appropriate response. And classically, like there are these encoder decoder models which decouple these. So usually we use like a large encoder to do the understanding part, and maybe a small decoder for doing the generation part. Whereas in LLMs, because of the decoder only architecture, this couples both understanding and generation. And we were hoping to understand if we can decouple the capacity required for understanding versus generation, and whether we can again use like maybe some kind of large encoder and a small decoder model, right? Okay, so the approach that we investigated is the following. So which is, we process the prompt using a large language model. So prompt, or like the input prefix, using a large language model, and then it generates some representations. And we use a projection layer to transform these representations into maybe a smaller dimension, which maybe which a smaller language model might be able to attend to directly in its attention layers, instead of it computing the keys and values for all the past tokens using its own parameters. And the main hope is that because these so because this large language model is more powerful, it might be able to generate representations which are more informative and can be more effectively utilized by the small language models. So one, it needs to adapt to this large language models representations, and two, because this is a large language models representation, the performance of SLM should improve substantially compared to what it was if it were using its own representations for keys and values inside the attention layers as well, right? So actually, so is the approach clear, exactly what we are trying to do, and how we are changing the attention layer? Any questions? I'll be happy to answer.
So the LLM is trained as before. So that part, that is fixed, and the new training will happen in the SLM and the projection layer.
Yes, that's correct. Yeah. So LLM is fixed. Again, like we investigated two things, but I think like the most viable setting seems to be the case where LLM is already trained and it is frozen, and we only train this SLM and projection layer, and use this info. Yeah. Okay. Okay, so we train this tandem model with models of different sizes. So the exact nomenclature of the models is probably not super important, but so we have like 3 model sizes, and we train a tandem model with like the large model being this largest one and the small model being this smallest one. And roughly speaking, what we want to see is whether this kind of combination of these largest and smallest model can outperform like an intermediate model, which will be either of like same quality, either like equalizing quality and then improving inference speed, or equalizing inference speed and then improving quality, right? So in terms of loss functions, we use the cross entropy loss with respect to the ground truth labels for training this small language model and the projection layers. We also use distillation loss and then compare with like a distilled version of the smallest model. And these are the comparisons that we do. So maybe so the first and third rows are comparison where we directly use like the ground truth based loss, and the second and fourth column are the ones where we use distillation loss in addition to the cross entropy loss. What we can see here is that on all the metrics on pre-training data, so we have like ground truth accuracy compared to ground truth, cross entropy loss with respect to ground truth, and relative accuracy and relative total variation distance. Both of these are with respect to the large model. So we see that on all of these metrics, like the tandem model achieves much better performance, higher accuracy and lower loss compared to the ones where we are just looking at like the small model by itself.
What is distillation loss?
So distillation loss will be that, so if you remember the cross entropy loss, we it's a KL divergence between the proposed distribution over the entire vocabulary and then the ground truth distribution. And the ground truth distribution, we take it to be a delta distribution at the ground truth label, and everywhere else we have zeros.
Mm-hmm.
And distillation means that we also have access to a large model. So this palm to bison is the large model in this case. So we take the output probability distribution over the entire vocabulary for that particular position of this large model and use it as target.
Okay.
Instead of like the delta distribution. So in general, so that is called logic distillation, and in general, like it has been observed to be very effective And even in this case, we see that it is effective. But the point to note here is that it seems like the kind of distillation we are trying to make here, where we are directly enabling this smaller language model to attend directly to this large language model's representations, this seems to be a much, much stronger form of distillation. So even when we compare like these two, where this column is logic distillation, and this column is there is no logic distillation, but we are enabling the small model to attend to large model, the performance of this like the tandem model, even with cross entropy loss, seems to be much better compared to the distillation loss approach with the base model.
And this is the fixed block length.
This is with a fixed block length. I think the block length was taken to be 3 or 4. I don't remember off the top of my head, but this is with a fixed block length.
But you would like something like so you wait till the SLM is sort of has a high I don't know, like high uncertainty, and then only plug into the LLM.
Yeah, that's a very good point. I'm not sure if I have those results in the slides, but in the paper we did do this adaptive block length experiments as well, and it gave some improvement. But I think in general, being able to predict whether we are like the small language model's prediction is going to be correct or not, that itself does not seem very easy to do. But to the extent that it was doing well, I think like this adaptive block length was working fine. Thanks for the comment, Piyush. Yeah. Okay, so these are some downstream evaluations, which again suggest that the tandem model, so in this column, is performing similar to this intermediate sized model while getting about like 1.16x faster inference compared to this intermediate sized model. Okay. So this was about like introducing the tandem architecture. But one thing we noticed is that the tandem model, like the tandem of small and large model, still has performance drop compared to the largest model. So one of the things that we would like to be sure about is that we are not affecting accuracy and only improving speed that we are getting. And there is a very influential paper called Speculative Decoding by Leviathan et al., which appeared in ICML 2023, which proposes actually a broader framework which can help speed up LLM inference while ensuring that the quality is not affected. And the main idea is the following. So there is a small model which is called the drafter model, and we input the query, and then it produces, say, some number of tokens autoregressively. So here it produced like 4 tokens autoregressively. So we take all of these 4 tokens and pass it through the primary model, and then ask what are the outputs, next token predictions, again conditioned on like every conditioned after every token, right? So until conditioned on it produces Himalayas. Until Himalayas, it produces E's, and conditioned until R, it produces A, and so on, right? And the first thing to note is that we see whether the output of the primary model agrees with the input to this model. And the first place where there is a disagreement, we note it, and here we see that like the first time they disagree is that the large model is saying we should have said the Himalayas is, and the small model had said the Himalayas are. So this is a disagreement. So we go back to the small model and correct this R to E's and let it regenerate from that point of view, that point onwards, right? And whenever there is like this mismatch, we are going back, and that's what we call backtracking. So as long as we are enabled to have enabled to reduce backtracking and have more agreement between the more agreement between the primary model and the secondary primary model and the secondary model, then the more higher the speed up that we get. Yeah.
No way to backtrack, because to backtrack you could keep running the larger models.
So here the important thing is that the large model is being run in a block of like these many tokens, right?
Oh, okay.
So you run, so the cost, so this will have matrix multiplications, but as we said, like matrix vector multiplications and matrix multiplications will take the same time. So the time it takes to process a single token is the same amount of time that the primary model takes to process this entire thing. And at the end of it, you are getting like 3 outputs, the Himalaya seas, right? So yeah, so in the time that the primary model would have generated 1 token, this has generated 3 tokens. So the additional overhead is, again, like we actually ran this small model auto-regressively for so many steps to produce this draft, right? So as long as that overhead is not very high and can be captured within, like for 3 autoregressive steps, it would have taken 3 times the primary model. Here it's only taking 1. So we have like 2 primary model runs, which are available to us to optimize. And as long as like this entire thing fits within that, we are getting a speed up. Yeah. Okay, so we want to be able to reduce backtracking, and then yeah, so if we reduce backtracking, maybe like all of these tokens will be accepted. So instead of like in one step, instead of accepting only 3 tokens, I would have accepted like 5 tokens here, right? So as long as we are able to reduce backtracking by producing drafts which are more likely to be accepted by the primary model, we'll get more speed up. And the main idea here is that like because the primary model is already verifying all of the past tokens, we can directly fit in like the Tandem model as a drafter here. So the secondary model, instead of being an independent model, if it can attend to large models representations using this projection layer, right, then the secondary model will be able to produce more accurate next token predictions, and this will have lesser probability of backtracking. So now maybe it has produced like couple more tokens more accurately. So the disagreement happens a bit later. So now in one pass, we are able to get like 5 tokens correctly, whereas earlier we were only able to get 3. So this is the kind of improvement that the tandem drafter can give within speculative decoding. Any question here? Okay. So we again did experiments on like the primary and secondary model being like a large palm 2 bison model, and the small model being a palm 2 gecko model. And so before sharing the results, so the baselines in speculative decoding are like there are many other drafter approaches that have been proposed for speculative decoding. So the first one is what is called parallel decoding. So where we have a either primary model, some large model, and instead of doing this fully autoregressive generation of next tokens, we just attach like small feed forward layers, which just take in the final layer representation and predict next token, 2 tokens further, and so on. But usually like the quality of these methods is not very good. And there are also approaches which draft based on retrieval. So we retrieve like sentences from some corpus and then look for like the longest matching prefix to predict like what the next tokens are going to be. Compared to both of these, the best known approach prior to our work has been using logic distillation to train a drafter model. And this is what we use for comparison. And it turns out that like on multiple data sets, we see that using different gammas, again, like we chose different block lengths depending on the data set. So we see that on all of the data sets and for different settings, including like how many samples we are generating, we are getting speedups from 1.1x to about 1.17x. And there are also results on using adaptive gamma, where we go back to the primary model only if we think that the drafter model's output is likely to be wrong. And I don't have the results here, but those results are in the paper. Okay, so maybe I can just conclude here and like mention some interesting directions for future work. So firstly, inference latency is a big bottleneck in the deployment of these very large and capable models. And I feel that there is still a very large room for improvement and is still a very active area of research. And in our work, we have proposed 2 different approaches. So one is called HiRE, which relies on leveraging sparsity of activations to speed up the autoregressive generation. And This one, we were able to get about like 1.47x speed up over a dense 1 billion parameter model with minimal loss in accuracy. And then the other approach is called tandem transformers, which is what I just presented. And the main idea here is to mitigate the autoregressive component by letting a small model generate autoregressively while enabling it to attend to the large model representations in its attention layers. And the architecture of Tandem itself seems fairly general and hopefully can be used in many other contexts as well, including, say, as an alternative to low rank adapters for fine tuning on small scale tasks and so on. Maybe I'll stop here. I'm happy to answer any questions.
I was a bit used. This is a long time, a lot of slides ago, but I was a bit confused about the matrix vector and the matrix thing. I can see why it would be more efficient to do matrix if you're multiplying the same matrix to a bunch of different vectors. Is that the case here?
Yes.
Why is that?
So that is the case because actually, thanks for the question. So let's go back to the beginning. Okay, so let's look at this feedforward layer, right? So it's parameterized by two matrices. So W2 is a matrix and W1 is a matrix, right?
Okay.
So if you have multiple tokens that you want to process at the same time, then you would concatenate, like you would just stack them beside each other, right? And then you will multiply, you will do a matrix multiplication between those two, right?
So these are multiple tokens that are candidates for the same position.
Multiple tokens in the same sequence.
W to W position.
Okay. So you will have a vector for this one, you will have a vector for this one, you will have a vector for this one, right?
Okay.
So, and this feedforward is exactly the same parameter. So you'll have W1 and then W2. So all of these are the same parameters, right? So if you are doing all this computation at once, then you would just do W1 times, like this would be the first column, this would be second column, this would be third column, like that matrix.
Okay.
Otherwise, you would only multiply W1 times this, you'll do all the computation, and then you'll come here, and then you'll again do the same thing, but they are sequential.
Okay. Got it.
Can you tell us a bit more about the HiRE? I mean, how there's this other thing, other way of speeding up, right? Which you're mentioning, HiRE.
HiRE.
Yeah. How does that speed up?
We can give you...
What is the idea behind HiRE?
Okay, so the main idea is that firstly, okay, so the main idea is just that we want to be able, so let's say this is like the softmax, this is the final softmax matrix, right? So we want to, like this will give us a probability distribution, but okay, let me introduce a little bit of background. So X is the final layer representation and Z is maybe the final softmax matrix. When we multiply this, we get the probabilities for different tokens, right? But we don't necessarily care about probabilities of all the tokens. We only care about probabilities for like the top few things, right? Because those are the things we are likely to sample from. So we want to compute this top K of, say, phi of Z transpose X effectively and like more efficiently. And the main idea is that instead of doing this full computation, multiplying this entire Z with this X, we first do a approximation of Z. We can either do it using low rank decomposition or quantization or any of those. And we compute maybe some top K prime by doing like this full multiplication. And we will use the full dimensional matrix Z and the full dimensional matrix X, full dimensional vector X on only these K prime things that we have identified. So roughly, we want to be able to speed up like the top K operator computation on the output of some matrix vector multiplication.
Yeah. Thank you.
So yes, from that, let's stand 20.
Thank you. Thanks, everyone. Bye.
Yeah, thank you for the talk.
Thank you.
I'm going to end the call.